Welcome to the deep dive. We're here to tackle complex ideas, pull out the key stuff, and, well, help you get informed without getting buried in jargon. Today, we're really jumping into the deep end with something called causal fermion systems. It's a pretty advanced piece of theoretical physics, and our goal, our mission for this deep dive is to figure out how this framework tries to connect three, massive puzzles in physics. We've got the standard model of particles.
Right, the particles we know.
Then there's chirality, this idea of handedness in particles, and maybe the biggest one, baryogenesis. Why is there stuff? Why all this matter and hardly any antimatter? Basically, why are we here?
Exactly. And for this, we're looking at excerpts from some research papers digging into this theory. They get quite technical, talking about things like octonions and exceptional algebras. Now, octonions, think of them as a really complex number system, way beyond the numbers you use day to day. And exceptional algebras are these, well, special mathematical structures with lots of symmetry. The core idea in these papers is that maybe these abstract math concepts aren't just useful tools, maybe they actually describe the vacuum of space itself and the particles in it.
And that's the really mind-bending part, isn't it? The potential aha moment here is that maybe the fundamental rules of the universe aren't just written in math, but they kind of grow out of the math itself, out of these deep structures. It's this huge quest for a unified theory, one idea to explain almost everything. And that could totally change how we see reality. So yeah, you should care. Okay, let's get into it. The foundational piece seems to be this vacuum state in the causal fermion system. So first thing, forget empty space. We need to imagine it differently, right? As something structured.
Precisely. Not empty at all. In this picture, the vacuum is made of what are called Dirac seas. Imagine these seas aren't just voids, but they're completely full of negative energy states. Every possible slot is occupied, like a completely full ocean.
An ocean for each particle type.
Yes, one Dirac sea for every kind of fundamental particle. And within this whole structure, the theory identifies 8 distinct sectors. Now, 7 of these sectors are basically identical. Think different particle families. But one is different.
Okay.
That distinct one is specifically for quarks. And crucially, in that quark sector, a property called chiral symmetry gets broken. That breaking is really important for how quarks actually behave.
And this is where I think the sources mention those octonions again. It sounded almost spooky how well they fit.
It is pretty remarkable. The papers point out that octonions, these weird 8-dimensional numbers, seem to act naturally on these exact 8 sectors. It's not something they had to force.
So it's not just a neat math trick. What does that mean?
Well, it strongly suggests there might be this deep inherent link, an algebraic connection between these really abstract mathematical ideas and the physical symmetries we actually see. Like finding, I don't know, a blueprint for the universe written in pure mathematics, a key fitting a lock you didn't realize was there.
Okay, so we have this structured vacuum, these sectors. Let's talk about chirality or handedness. Particles have this property. It affects how they interact. How does this framework handle something so basic?
Well, here's a really interesting point from the sources. Chirality isn't something the theory predicts or derives.
It doesn't explain why particles have handedness.
No, not yet. Anyway, it has to be assumed. It's put in as part of the setup, part of how the vacuum is configured from the start.
So that raises a big flag, doesn't it? If it's fundamental, why assume it? Is that like a known gap or?
It's definitely a point the researchers acknowledge. It's currently an assumption needed to make the rest of the theory work correctly. They hope to derive it later, perhaps. But the consequence of assuming it is vital. You absolutely need a left-right asymmetry, specifically in the neutrino sector, within this framework.
Why? What breaks if you don't have that asymmetry?
If you don't build in that handedness, the theory just can't reproduce the right gauge groups of the standard model. Those are the fundamental symmetries controlling forces. And also wouldn't get the couplings right, how strongly particles interact, or the mixing matrices, which describe how particles like neutrinos change type. The whole picture falls apart without assuming chirality.
Okay, so that assumption has big knock-on effects. What about neutrinos then? They're notoriously weird particles. How does this specific requirement for handedness affect them?
It leads directly to a really significant prediction. At least one type of neutrino must have mass. It can't be massless.
Now, why is that?
Because according to the theory, if all neutrinos were massless, it would violate the conditions needed for the vacuum state to be stable, to minimize what's called the causal action. That's the core principle driving the whole system. So the very stability of the vacuum in this model demands that neutrinos have mass, which, fits perfectly with what experiments have been telling us recently.
Right. The discovery of neutrino oscillations showed they must have mass, so the theory aligns there. Okay, let's shift gears to maybe the biggest cosmic mystery, baryogenesis.
Ugh.
Why is there all this matter around us and basically no antimatter? Why did one win out over the other? How does this causal fermion system try to answer that?
Okay, so the picture this theory paints of the very early universe is quite different. It starts with that Dirac sea we talked about, but it's completely full. Every negative energy state is occupied uniformly.
Right, a full C. Then what?
Then the universe expands. Think post-Big Bang during inflation, as structures start to form. The theory suggests that as space-time evolves, fewer states are actually needed for the Dirac sea to maintain its structure. So some states effectively get emptied out. But they don't just disappear. This emptying process leaves behind a surplus of states, and these emerge as the positive energy matter we see.
Ah, okay. So it's like draining a full tank, but the residue left behind becomes matter.
That's a decent analogy, yeah. The crucial difference here, compared to standard physics like the Dirac equation, is how this matter appears.
Because usually creating matter also creates an equal amount of antimatter, right? A particle-antiparticle pair pops into existence.
Exactly. Standard processes are symmetric. But here, the corrections coming from the causal action principle, that fundamental rule governing the system, are the key. These corrections specifically allow for matter states to be created without necessarily creating a corresponding antimatter state at the same time. It breaks that symmetry.
That's the linchpin then. That's how it generates the imbalance.
That's the proposed mechanism, yes. It provides a way to get more matter than antimatter. The source does mention that this is compatible with the general conditions needed for baryogenesis, the Sakharov conditions, things like CP violation.
Which is that asymmetry between matter and antimatter behavior.
Right. But they also stress that a lot more quantitative work is needed. They need to calculate the exact amount of matter predicted and see if it matches what we observe in the cosmos. That's still a big step.
It still sounds incredibly ambitious, though, trying to link all these things. And you mentioned earlier, it seems very elegant at its core, potentially having just one fundamental parameter. Is that right?
Well, fundamentally, yes. The causal action principle itself, the engine of the theory, really only has one free parameter, usually called kappa cap. And this single parameter is supposed to set all the essential scales, like the relationship between the Planck length, the tiniest possible distance, and the Compton length, which is tied to a particle's mass. On paper, that's incredibly simple and elegant.
One parameter to rule them all? Sounds amazing. But there's always a but, isn't there? What's the catch in practice?
The catch comes when you try to actually model the vacuum state we discussed earlier. Well, the principle has one parameter. Setting up the specific vacuum configuration introduces more.
Ah, okay. Like what?
Well, things we need to match reality. You end up needing parameters for the known particle masses, the neutrino masses specifically, and also these things called regularization parameters.
Regularization parameters, what are those about?
They come in because the theory assumes space-time isn't smoothed down at the tiniest scales near the Planck length. It assumes it breaks down into something discrete, like pixels, instead of a continuous image.
Okay, like a quantum foam or something?
Sort of, yes. And regularization is basically the mathematical toolkit you need to handle that transition, to smooth things out so you can connect that tiny discrete picture to the continuous physics we see at larger scales. But that process, that smoothing, inevitably brings in extra parameters that are linked to the physics we don't yet understand at the Planck scale.
So, the underlying principle is simple, but building the actual model adds complexity back in because we have to plug in some unknowns from observation or handle the breakdown of smooth space-time.
That's a good way to put it. The elegance is still there in the principle, but practical application requires these extra inputs for now.
So, given these challenges and the theory's ambition, what are the next big steps? What are the researchers aiming for, according to the sources?
The main goals outlined are pretty concrete. First, they really want to use this framework to figure out the precise mathematical description, the metric of the very early universe. And then using that metric, calculate the rate of baryogenesis predicted by their mechanism. How much matter should have been created according to the causal fermion system?
And then compare that number.
Exactly. Compare it quantitatively. See if it matches the amount of matter we actually observe in the universe and how it stacks up against other existing models of baryogenesis. It's about rigorous testing against data. Does it just sound good, or does it actually work?
So quite a roadmap ahead for them. We've really covered a lot today, exploring this causal fermion system idea. It's trying to do something huge, connect the dots between particles, the vacuum structure, fundamental symmetries like handedness, and even the origin of matter itself. all potentially flowing from deep mathematics.
It really shows you where physics is constantly pushing, doesn't it? Frameworks like this, even if they're not fully proven yet, are vital. They force us to question our assumptions, look for deeper connections, try new mathematical tools. It's how we explore the edges of what we know about reality.
Absolutely. And maybe the final thought to leave you, the listener, with is this. Just consider how the deepest secrets of the universe, why things are the way they are, might not just be described by math equations, but could actually be mathematical structures. Imagine reality itself emerging from something as seemingly abstract as octonions. It's an idea that really challenges our everyday intuition about what's real. Something to ponder.